All right, so let's get some of these filled in. So chapter 2, we're going to talk about the polynomial and rational functions. Okay, so in section 2, a polynomial function of higher degree. So the graph of a polynomial function is continuous. So what do we mean by continuous? Well, it essentially means that the graph of a polynomial function has no breaks, holes, or gaps. So you're not going to see any holes. That's a hole. You're not going to see any breaks. That would be or gaps. So the graph of a polynomial function is just going to be continuous. It's not going to stop. The way to think of this is if I start drawing the graph, if I keep my pencil on the paper, I'm not going to pick my pencil up. It's going to stay on the paper the whole time. That's continuous, okay? The graph of a polynomial is also smooth, meaning that there are no sharp turns, okay? So a polynomial function is not going to look like the graph of an absolute value where you got this little point at the end. It's going to look like things like this that are smooth. They're going to have rounded out edges. Okay? Monomial functions with even exponents are parabolic. However, they get flatter at the vertex the higher the exponent. Okay. So we know that if the exponent is even, it's going to be parabolic because the simplest one would be x squared, our quadratic function. Quadratic function is a parabola. So the graph of x to the fourth is going to look very similar, only as it comes down it's going to get flatter. So it's going to look closer to like this, as opposed to this one would be f of x equals x squared. This one is f of x equals x to the fourth. Okay, so it's going to get flatter as it goes down. And so, again, I'm just sketching these. This isn't with real precision. You know, you'd have x to the sixth.
But is it still only going to touch at one point?
Yes, that's a good point. It's still only touching at one point. It's just getting flatter as it goes, but because I have this big stylus, you can't really see. It looks like the whole thing's on the exit. So again, x to the 10th. So they're going to look flatter like that. So as the exponent gets higher and they're even, they're going to come closer. They're going to look more and more like a horizontal line the higher it gets. It'll never get to be a horizontal line. It'll always be that parabolic graph. That's why yesterday when we did that one problem, I told you could pick any vertex you want. Because depending on where you make your vertex is going to depend on how short or how wide that parabola is. Okay? So there's an infinite number of ways you can draw these. And your function is just going to depend on how flat that gets at the vertex, okay? And it doesn't have to be an exact sketch, but they want you to understand the idea that the higher that exponent gets, the flatter it's going to come down to the horizontal axis, but it will never actually get to be a flat line. If I did f of x equals x to the 1 millionth, it would, on your graph, look like a flat line because on your graphing calculator, you can't see that in a large enough viewing window. But if you could go out to 100 million places, it would still look like the parabola, okay? All right, monomial functions of odd degree will have the same basic shape as not GHE, the cubic function, although it will become flatter near the turning point. So in the cubic function, we have a sort of a half of a parabola on the top and then the other half going the opposite way on the bottom. And where that turns is we call that a turning point. Okay, I don't think that's in your notes, but we call that a turning point. And so the higher those exponents get, the flatter we'll get towards the turning point. So, for example, x to the fifth is going to look more like, like that. Again, you're still only crossing the x-axis at one point. So it's not going to lie anywhere. It's just going to look flatter. Okay? Same thing with the other. So x to the seventh. And then again, I just picked numbers at random here, but so it's almost going to come in. Let me get back to this. See, this is going to get flatter. Again, it's never going to come to a flat line, but as this number gets closer and closer as it goes to infinity. As that gets higher and higher, it's going to look closer to a flat line. Okay. That part is simple. So we have this leading coefficient test. So when we have a polynomial, as x moves without bound to the left or the right. So that means that once you have your graph, as you go to infinity or negative infinity, that's what that means. Without bound to the left or the right means your graph goes on to infinity, or negative infinity comes from negative infinity. We want to know what's happening to that graph. So the polynomial function f of x equals a sub n x to the n, and this is just our polynomial in degree order. And so again, our highest exponent is going to go first all the way down, and where it's not 0, because you're not going to ever use 0. Okay? So when you put that in order, you can do a leading coefficient test. So the idea is this exponent here and this is your leading coefficient here, a. This exponent up here, your highest exponent you have is going to be your degree. So if you have x to the 15th and then whatever else after that, it's a 15th degree polynomial. Whatever your highest exponent is your degree. And so you need to know what your degree is, and you need to know what your leading coefficient is. And if you know what those two things are, you're going to know what's happening as these things go to infinity. That's the idea. All right, so when n is odd, that means when your degree of your polynomial is odd, x to the third, x to the fifth, x to the seventh, when your degree is odd, then you look at your lead coefficient. If your degree is odd and your lead coefficient is positive, well then it's going to look like this. The graph is going to fall to the left and rise to the right. And so I put these little dash lines because the little dash lines just say that it doesn't matter what's going on in between there. But ultimately, once all that stuff is done, it's going up to infinity and it's going down to negative infinity. So it's falling to the left and rising to the right. So give me an example, Kelly, of a function that's going to do this. It doesn't have to be this function of this particular graph here, but give me an example of that. Just any function. F of x equals, I want you to give me any function that will fit this. The coefficient, the leading coefficient, we want it to be positive, and we want it to be an odd degree. So it could be anything you want.
3.
What's that?
Could it be 3 something? I don't know.
Pick a number.
X.
So we want it to be positive. So any positive number. So pick any positive number.
3.
3. Very good. Okay. X to the what? Because we want it to be odd. But it could have been anything. As long as this number is positive, as long as this is an odd number, so this particular graph is the cubic function with a horizontal stretch of 3, right? That's what that is out front. So it's going to look like this. And you're going to see that it falls to the left and rises to the right. That's the function that you gave me. It looks just like that. Okay? Any function where this is an odd degree and this is a positive leading coefficient is going to have the same endpoints. They're going to happen. Different things will happen in the middle. That's why I did this thing here. This dash line just means all kinds of things can happen. You can have 25 turns in here, depending on what you have, how long your polynomial is. But they're all going to end with the graph rising to the right and falling to the left. Okay. If it's also odd, but this time if it's a negative leading coefficient, then it's going to do the opposite. It's going to fall to the right, and it's going to rise to the left. So it's basically just the opposite. And if you think about it, pick me a function that will fit this. Okay.
-1.2.
All right. It's going to be hard for me to draw, so let's just go with -1.
All right, -1.
X to the...
Third.
Okay. Say it with some conviction. It's just got any odd number. You can say x to the 25th. It doesn't matter. And you could have said, by the way, x to the 25th plus 3x squared minus 2x plus 7. It's still going to do the same function. What all that other stuff's going to tell you is what's happening in between. So this particular function you gave me is the cubic function, only it's the negative one. So what's that going to look like?
What you drew.
It's going to look like that one. So notice it's the opposite. Notice that this graph rises to the left and falls to the right. So as it goes to infinity, it goes to the right. As it goes to infinity, the range value goes to negative infinity. In other words, the y's go to negative infinity as x goes to infinity. And on the left-hand side has the x's, it's going to rise to the left, which means that as it comes from, on the x-value from, because it comes from negative infinity, as it comes from negative infinity, it is going to negative infinity. Just describing the graph. Anything, depending on what else you have here, anything can happen in the middle. It's pretty simple, right? So by knowing the degree and knowing the leading coefficient, you have an idea of how the graph ends. And you say, why is all this important? Well, it's important because when you're looking at these on a graphing calculator, if you have to make sure that they're ending in the same way, so you're looking at the viewing window to see your maximums and minimums. So if you just, for example, did a graph and it looked like this, or only had this part, it wouldn't necessarily, or if let's say I did it in my viewing window look like this. This would look like I'm falling to the left instead of rising to the left. So you want to know which way these are going. All right, so it's the opposite if it's even. So if your degree is even and the leading coefficient is positive, then the graph rises to the right and to the left. Okay? And we know this because what's the most basic function that we have for an even positive function with an even degree and a positive coefficient? What's the simplest one we have? Y equals x squared, which is simply the parabola. Okay? And then the leading coefficient is negative, like negative x squared. It's the same thing, only it's falling to the right and to the left. Okay? So, once I know those tests, basically, I'll know how all these graphs finish. So let's do some together. Okay, we'll start with you, Ben. So I have negative 2x to the 7th minus 42x to the 4th plus x minus 1. So what's going to happen at my ends? Tell me what this graph's going to do.
Wait, can you have any combination?
You
of
can add
those
anything.
four?
Yep. You can add anything you want. I could let you guys make up these numbers. I just
No,
made these
I
up
mean
on my
like
head.
based on like the four things you just gave us, it can be any combination of
Yeah.
those four.
Right, because all you're concerned with is two things, right? I can sit there and write an equation from here all the way to here and continue on the board all the way up to Mr. Arnold's room, and it doesn't matter. I'm only still looking at two things. What am I looking at?
The degree.
The degree and the leading coefficient. So you can do this one, Kelly, to start. What's the degree of the first one here? What degree polynomial? It's a 7th degree polynomial, which is also an odd polynomial. And what is the leading coefficient?
-2.
Which is negative. Okay, so my leading coefficient is negative. I'll just write lead for there. And my degree is odd. So when I have an odd degree. I don't know why it grabs my eraser. All right. So if I have, don't graph it. I want you to be able to do this without, because I know you guys can look these up on a graph, but tell me what this is going to do.
I don't know though.
All right, well, put it this way. It's going to do the same thing as the ones you know. So let's pretend you don't want to memorize all those rules I just gave you. Okay, because I've used them enough times that I know what they're going to do, but pretend you don't. The lead coefficient is negative, okay, and it's an odd degree. So what function do you know that has an odd degree that has a negative coefficient that you do know?
Cubed.
What is it?
X cubed.
With a negative lead coefficient.
Oh, negative x.
All right, it's going to do the same thing as negative x cubed is. So if you didn't memorize those rules, all you can do is write down negative x cubed, and it's going to have the same, this graph's going to start and end the exact same way as x cubed. It's going to rise to the left, and it's going to fall to the right. And I didn't graph that out, but did you graph it out?
Not yet. 'Cause
You
you
know,
said not.
if you throw that in there, it's going to, now, the graph when you put in there, I should have put dash line, because it's going to do all kinds of crazy things in the middle. It's not going to look like the cube, but it's going to end and start like it.
So
And that's all we're looking for in this section.
all you really have to know then is whether it's negative or positive?
Whether this is negative or positive, and whether this is even or odd.
So
Yes,
No.
that's all you have to know. And they're going to try to fool you, because they're going to throw in all these things, and all this other stuff is just gravy after that.
And they're gonna make like this huge equation, and they're gonna put the highest coefficient. Let's say the highest coefficient is 16 x to the 8th, and they put that in the middle of all other coefficients where the highest exponent is like 6. That is the whatever
The highest exponent. Right, if they gave you one where it wasn't in order, you mean?
Yeah.
Yeah, I don't think they do that in the book, but they could. If they did that, that's just out of order. Because when we write it properly, you always write them. That's the definition of the polynomial. You write them from the higher degree to the
Yeah.
lower one. But if they did, yeah. So if somebody did an equation and they left it in improper form and they told you it's x plus 3x cubed minus x to the 7th, it's still a 7th degree polynomial. It's just not written the way we want it to be written. So that wouldn't matter. Okay, so what's this graph going to do, Ben? How's it going to start and finish? That's really all I care about.
Like positive x squared.
It's going to start just like, right, very good. So if that's that, you know that it's going to, I don't know what's going to happen in the middle here.
Do we need to know?
Well, I know, because there's nothing after it. It's a vertical stretch of 16, so it's going to be really thin.
Yeah, but
and its x to the 8 is going to get real flat at the end, so it's going to look something like this.
Are we gonna?
It's going to look like a U. That's going to look something like that.
Are we gonna need to know, like, for the first one, are we gonna need to know how it's gonna?
Not right now, not for this chapter. Eventually, if you go into calculus, then you get graph functions. You have to sketch functions by hand. I don't think that's in your book, so I don't think you'll get to that this year. They don't get to that this year, do they? Looking at this and just have to graph what it's going to look like. I don't think they're going to have to. Without a graph, I don't think they're going to have to do that.
No.
In calculus, you'll use test points and you'll know when it changes and all kinds of things. But we're not going to worry about that today. Today, all we're worried about is how's it going to start and finish.
Okay.
All right, Kelly, how's this one going to start and finish? The third one.
It's gonna be like x cubed.
Just like x cubed. Yep. And so if you think of it this way, you don't have to learn all those rules, okay? You know, once you use them for a while, you'll just automatically know, well, if it's positive in this degree. But yeah. Now, I don't know what's going to happen in the middle here. Actually, I know what's going to happen, but you're not going to know what's going to happen in the middle here. But you are knowing that it's going to rise to the right and fall to the left, just like x cubed does. All right, finally, Ben, the last one. How's this one going to look? How's it going to end? This is what I'm going to do. I'm going to put all these dots because we don't know what's happening in the middle. But how's it going to start and end?
Negative x squared.
Just like negative x squared is. What does that look like? A frowny face, right?
How come whenever I say that, you're like, well, parabola.
Look. So I don't know what's happening up in here with my 3x. Well, I do. It's going to look sort of like it does. That's what it's going to kind of look like. But you don't need to know that. All you need to know is it's going to fall to the right and the left. Does that make sense? All right. We made that, got that in plain vanilla?
Yeah.
Very good. Let's see what else we have.
Uh-huh.
The following are true of a polynomial function f of degree n. The function f has at most n real zeros. All right, well, what does that mean? If I pick a polynomial, give me an example, Kelly. We'll just pick one. Any polynomial you want to think of.
I don't think well on the spot.
There's not a right or wrong answer. It could be any polynomial.
X squared.
Let's make it a little more difficult, though.
Plus
That's fine. Plus.
3x minus 7.
Okay.
Is that bad?
What? Oh, no. What degree is that? What's that degree is that?
Second.
Second degree. The most it has is 2 real zeros. What's a real zero? A real zero is just how many times it can cross the axis, the x-axis. Okay? So at most, it can cross it twice. And we know that because it's a parabola. That doesn't mean it has to cross it twice, because we've learned from history, it may not cross it at all. If your vertex is above the x-axis, it may not do it at all. So this doesn't say it has to do it 2 times. All it says is at most. So all you need to know is, if a function is of second degree, the most times it can cross the x-axis is 2 times. It can cross it 1 time, meaning that the vertex would be on the x-axis, or not at all, if your vertex is above the x-axis. But if it's below the x-axis, it's going to cross twice, and that's the most it can cross. And because it's a parabola, it's the only way it can. Okay? That's all that's saying in late terms. If I have x to the 7th, if I get f of x equals x to the 7th, the most times that can cross is 7 times. It can cross the x-axis 7 times. I can have 7 real zeros, where y is 0. A real zero is where f of x is the same as y. Y is 0. That's what a real zero is. The graph of f has at most n minus 1 relative extrema. Okay? So relative minima or maximum. So an extrema just means a relative minimum, a minima, or maxima. Okay, so I want you to give me a polynomial, Ben, but make it a higher degree. So
4x to the 5th
4x to the 5th
plus
plus,
x cubed
sure,
plus 2. I don't know.
plus 2. Outstanding. All right. So what does that tell me? How many times is it possible for this to cross the x-axis?
5.
5, because the most it can have is 5 real zeros. If I take my degree minus 1, so it's a 5th degree minus 1, it can only have 4 at most, relative minimum or maximum. So what does that mean? It's 4x to the 5th, so it's going to look like it's going to start and end like the cubic function. You're minusing a cube, and you're adding 2. So your actual graph is going to look like
What?
something like that.
You knew?
It's something like that. Again, I'm
Close.
sketching. It's going to look close to that.
Oh.
So this is going to cross 3 times. Notice it doesn't cross. It doesn't cross 4 times. But based on these numbers here, if this was a 4th and a 3rd, if they went down evenly, 4, 3, then this loop here would come down and cross, and then it would cross 4 times. But this particular one you gave me crosses 3 times. So it doesn't mean that it has to have. And these are your maximum and your minimums here, right? So you got, I'm not an artist. So you got 4. This is a relative maximum, right? Because you increase and then you decrease. This is a relative minima because you decrease and then increase.
Oh.
This is a relative maximum here. This was from the first chapter, right? Where you increase and then decrease and then. So you have 4 in this particular graph. That's the most you can have is 4. The most times you can cross the axis is 5. This one only does 3, but it could have went 5. The most you can have for relative extremity is 4. Okay? So why are we learning this? The reason is so that you understand when you graph things and when you're doing problems, you'll know how many places is my viewing window okay. So for example, if you graphed this thing and on your graph it came up, and that's the only picture it showed you was in here, that would tell you I'm not looking at the whole graph. More things are happening. There's more possible extrema. There's more minimums and maximums. I have to increase my viewing window to actually see what's happening in the whole graph. Or if you're solving a problem, you have an idea. If I'm looking for my real zeros, what this chapter is about, or in the last one where I was looking for those maximums and minimums with the diving board. The diving board is a simple function, but you might have a cost function, a stock function, where it does this. You see stock charts on the TV when they show it on the stock channel and they go up like this and jagged. They do those in functions. You need to know, what am I looking at? What would I expect to see? So you start to get an idea of that. Okay, let me quickly.
I didn't even know a stock channel existed.
No,
I'm just going to do a stop start real quick. Otherwise.